This video is one in a series of videos where we discuss the complete analysis of a heat engine, refrigerator, or heat pump. In this particular video, we're analyzing a heat pump. What distinguishes the different devices are two factors. First, the direction in which we go through the pressure versus volume plane. In this case, A is our starting point, then we go through B, and finally to C before returning to A. This cycle goes in the counterclockwise direction, and as always, clockwise is for an engine and counterclockwise is for a heat pump or refrigerator. We can understand why this is true in a very simple manner. Any system would prefer to expand at the highest pressure and contract at the lowest pressure. This would be a clockwise motion, and the system would be doing what it wants, delivering work to us by expanding under high pressure and then contracting under low pressure. However, in this case, this system will expand under the lowest pressure and contract under the highest pressure. This can only be accomplished by us supplying work to the system and not the other way around. In this case, the work from the system will be a negative number, and this will indicate that the device in question is either a refrigerator or heat pump. The features that distinguish these three cases, engine, refrigerator, and heat pump, will become clear to us as we approach parts C and D of this problem. They will not make any difference whatsoever to parts A or B. In order to proceed in an efficient manner, we're therefore going to ignore the distinction between engine, refrigerator, and heat pump until we get to parts C and D of the problem. Let's read the problem in question. We have 2 moles of nitrogen gas. Please note that nitrogen gas is diatomic, and this will make a difference when we choose C sub V and C sub P. And these 2 moles are taken through the cycle shown in the figure below, A to B to C, and finally returning to A. The device is to be used as a heat pump. At point A, the temperature is 300 Kelvin, the pressure is 300,000 pascals, and during the process A goes to B, the volume of the system doubles. In part A, we are asked to calculate and fill in a so-called state table. This is called a state table because the 3 columns, pressure, volume, and temperature, are state variables. And in order to solve for state variables, we will recall the equation of state, PV equals nRT, which is the relationship between the state variables. Immediately we can see that for point A, we're given a variety of pieces of information, namely that the temperature is 300 Kelvin and the pressure is 300,000 pascals. What we understand is that anytime we have 2 out of 3 of these variables, as well as the number of moles, we're going to be able to solve for the third. In this case, the ideal gas equation, our equation of state, can be rearranged to say that the volume is nRT over the pressure, and using the fact that we know that N is equal to 2 moles, we'll be able to immediately calculate the volume at point A. The result we get is 0.01663 cubic meters. We're keeping a lot of digits because we know at the end of this problem, in order to get an accurate result, we are going to have to accurately subtract 2 rather large but close to one another values. In order to have an accurate result, we need to keep plenty of significant digits, and in this case, I've actually kept them all. What else are we told in this problem? Well, we're told that the volume of the system will double in getting from A to B, and so in that case, we simply double the volume at A to get the volume at B, yielding 0.03326 cubic meters. In order to understand any other value at point B, we need to understand how point A is connected to point B, and so we refer back to the original problem. The figure shows that A and B are connected by an isothermal curve. That means that every point along this curve, including its endpoints A and B, has the same temperature. Since the temperature at A was equal to 300 Kelvin, that immediately means that the temperature at B will also be equal to 300 Kelvin. Once again, we have a situation in which 2 out of 3 of the values in line B are available. Therefore, we can calculate the third value using pressure equals nRT over V, and the result of this will be 150,000 pascals. Please note that we could have gotten this same result a second way. We could have used the PVT relation for an isothermal to relate pressure and volume at moment A to pressure and volume at moment B, and we would have gotten exactly the same result. In order to understand point C, we will again refer back to our original figure, and we notice that C is connected to B by a constant volume process, therefore they will have the same volume, and C is connected to A by a constant pressure process. Therefore, we can copy the pressure at A for point C and the volume at B, and that will once again give us 2 out of 3 along this line. When we have 2 out of 3, we can solve for the temperature is PV over nR, yielding a result of 600 Kelvin, or we could have used the PVT relationships either from B to C or from A to C. This completes the state table calculation, and notice that on an exam the state table would be worth 9 points, meaning that the state table is 1 point per value. They have to be correct, otherwise you don't get the point. To advance further in this problem, we're going to need to calculate the so-called process table. The process table uses the formulas for work, heat, and change in internal energy as found in so-called the table. And the table is found in another video and in your lecture notes and looks as follows. The table has 4 rows, one for each process, constant pressure, constant volume, constant temperature, and adiabatic, and 3 columns for work, heat, and change in internal energy. Because our diagram has the 3 processes, constant temperature from A to B, constant volume from B to C, and constant pressure from C to A, we'll be using the first 3 rows of this table in our calculations. The process A goes to B is isothermal, and anytime we calculate any of these rows, it's easiest if we find that one of the 3 values is 0. Because temperature is related to internal energy, when you don't change the temperature, you don't change the internal energy, and therefore the change in internal energy from A to B is 0, meaning that we can calculate either Q or W and know the third because we'll have 2 out of 3. The first law of thermodynamics, delta U equals Q minus W, will be used to calculate the third when we have any of the 2. As you can see, when delta U is equal to 0, Q is equal to W, and therefore we will be using a single formula. I remember it most easily for W, that the W during a constant temperature process is nRT, natural log of V2 over V1. In this case, volume 2 is volume B, volume 1 is volume A, and we'll be able to easily calculate the amount of work done as 3458 joules. When delta U is 0, Q is the same as W, and therefore the heat transfer is also 3458 joules. Next we examine B goes to C. B goes to C is a constant volume process, and constant volume process also has a 0. The 0 for a constant volume process is the work, because work is pressure times change in volume, and we didn't change the volume. Therefore, for the constant volume process, the heat and the change in internal energy are the same number. The formula for either one of these is NCV delta T. We recognize that this formula contains the molar specific heat at constant volume, and that quantity depends upon the type of gas that we have. This problem uses nitrogen N2 gas, meaning that it is diatomic. We remember that for a diatomic gas, C sub V is 5/2 R and C sub P is 7/2 R. If we had been using some other type of gas, we would have used different values for CV and CP. In order to plug in numbers, we're going to have to understand the value of delta T. Delta T is final minus initial. The final temperature from B goes to C is the temperature at C of 600, and the initial temperature in B goes to C was the temperature at B of 300. Therefore, we can plug in all of these results and get 12,473 joules. And this result applies also to the heat. The last line to be calculated before we check our totals is process C goes to A, where C goes to A is a constant pressure process. Unfortunately, in the constant pressure process, there are no zeros among W, Q, and delta U, meaning that we're going to have to perform 3 calculations. The calculation for delta U is the most straightforward because the formula for delta U is the same no matter what process you have. For the problem at hand, the process C goes to A has A as its final and C as its initial. Therefore, the delta T from C goes to A is the temperature at A minus the temperature at C, meaning that the delta T is negative 300. As a result, we're going to get negative 12,473. For the heat transferred during the process C goes to A, we'll also be using a delta T sort of formula. However, this formula uses NC sub P times the change in temperature. Because the C sub P is 7/2 R rather than 5/2 R, we get a larger result, but still negative for the heat flow in C goes to A. That result is negative 17,461. Finally, for the work from C goes to A, we're going to use the work formula. The area under a straight line is a rectangle, so that's going to be the height of P times the V2 minus V1. Since we are going from C to A, volume 2 is volume A. So the pressure times volume A minus volume C is going to be a negative number, and the amount of work we get in this case is negative 4989 joules. The final line in our process table is found by totaling everything that occurred before it, and this line gives us the opportunity to check the quality of our calculations leading to this line. Simply doing the totals, we'll find the following results. The total work appears to be negative 1531 joules. The total heat appears to be negative 1530 joules, and the total change in internal energy is 0. This is a good result. The reason is the following. We know that any time we complete any full cycle, the total change in internal energy must be 0. Since we returned to the original state, we returned to the original temperature, and the total change in temperature is 0. Therefore, the total change in internal energy must be 0. Whenever delta U is 0, Q should be the same as W. Now, we got them close. And this is what one calls close enough. On a final exam, or any exam, when you get these two numbers that are supposed to be identical and they are slightly off, it means you had a little bit of round-off error, which we did. That's totally okay. Keep this and proceed to the final calculation. Finally, we recognize that not only are W and Q equal to one another, but they're negative. This is a very important point. Whenever you have an engine, the engine does positive work. When you have a heat pump or a refrigerator, the work is negative because the work must be supplied by you. You have to plug in the refrigerator in order to get it to run. It doesn't run you, you run it. As a result, the negative value of both Q and W is expected and correct. This becomes important when we move on to part C of the problem. In part C, we are asked to calculate the heat from the hot reservoir and the heat from the cold reservoir. In order to do this calculation, we now have to understand what kind of a device we're running. Are we running an engine, or are we running a refrigerator/heat pump? The engine is the situation we consider to be most natural. The engine takes in heat from the hot place and dumps heat to the cold place in order that some amount of work can be done on the outside world. This is how your gasoline engine works. However, a refrigerator or heat pump is exactly the opposite. By performing work and forcing the cycle to go in the reverse direction, we are able to take in heat from the cold place and we are able to push out heat to the hot place. And so, for a refrigerator or a heat pump, the Q of the cold place is a positive number because you flow in from the cold. And the Q of the hot place is a negative number because you flow out to the warm place. In order for us to correctly solve this problem for both the values of Q hot and Q cold, we're going to need to reference our table of all the processes. We recognize here that Q hot is going to be the place where heat is dumped, and as a result these will be negative heats, and there's only one of them, minus 17,461 joules. The cold place is where you take heat in, and we notice there are two contributions to heat coming in, both process A to B and process B to C, meaning that the total Q cold is equal to the sum of 3458 and 12,473, leading to the result 15,931 joules. Lastly, we're to calculate the performance coefficient of our heat pump. And to do this, we need to retrieve three summary pieces of information. The three summary pieces of information are the work, which was negative 1531 joules, the Q hot, which was negative 17,461 joules, and the Q cold, which was positive 15,931 joules. Once again, the answer to this part of the problem depends upon what kind of a device that we have. For each device, whether we have an engine, a refrigerator, or a heat pump, we have to decide what it is that we get as a result of running this device and what we used to pay for it. Performance, whether it's efficiency for an engine or whether it's a coefficient for the refrigerator or heat pump, is always defined as what you get divided by what you pay for. Let's examine each row. We made an engine because we wanted to get some work. We paid for it by drawing heat out of a hot place. As a result, what we get over what we pay for is the work divided by Q hot. Next, we built a refrigerator, not for the purpose of using electricity, but for the purpose of cooling our food. As a result, what we get from our refrigerator is Q cold. What we pay for it with is the work taken in the form of electricity from the wall, and so the performance coefficient of what we get over what we pay for is going to be Q cold divided by the work. Finally, for a heat pump, the reason we built it was in order to warm the living room. So we have achieved Q hot, pulling the heat out of the January air, but we paid for it, just like the refrigerator, by doing work. So the performance coefficient will be Q hot over the work. It's important to note the range of each one of these parameters. For an engine, the efficiency goes from 0 to 1, because you can't have more than 100% efficiency, even in your imagination, for an engine. However, for a refrigerator and a heat pump, ideally you'd like to move the heat without doing any work. Therefore, both of these coefficients should go from 1 to infinity, and when you get your final result, you can check whether each one of these fits in the appropriate range. The problem that we have at hand is a heat pump, and therefore we read off that the performance coefficient is going to be QH over the work, and for our numbers this is going to be negative 17,461 over negative 1531, resulting in a performance coefficient of 11.4. Now, let's think about what this performance coefficient means and why this device is so attractive in terms of being an energy efficient device. For every 1 joule of electricity that we use to run our heat pump, we place 11.4 joules of heat into the living room because we stole the rest of the heat out of the cold winter air in order to warm our living room. That's pretty amazing, and that's what a heat pump is.